What if we were looking at spending $20,000 for a new car and the interest rate was $8,000 per year compounded monthly? If we took out a 4-year loan, how much would we pay every month for that car? Well, we can see here that we have our computer formula here, our calculator formula here, and our Excel formula here. So our monthly 8% is 0.66667% per month, 48 months. So our 4-year loan period, 4 times 12, our total loan is 20,000. So our monthly payments would be $488.26. If we wanted to know how many payments we needed to make in order to pay something off, so think about this. We have $1,000 due on our credit card. We pay $20 a month. Our rate is 1.5% per month. If we only pay the minimum on that $1,000, it will take us 7.75 years to pay off that $1,000 at $20 a month. And that is assuming we don't put any more money on that. So that's considering the amount that we pay and the compounding interest and the total amount due. So remember that when we're looking at how much debt we take on, that compounding interest keeps adding that debt on every single month. And if you're just paying the minimum, it can take you a very long time to pay off that debt. Also looking at the number of payments. What if we borrowed $2,000 at 5% and we're going to make annual payments of $734.42? It would take us 3 years to pay off that loan. We can see here, looking at the result from the calculator formula, that the result is 3 years. What if instead we were trying to find the rate? Suppose we borrow $10,000 from our parents to buy a car. We agree to pay $207.58 per month for 60 months. What is the monthly interest rate that we are agreeing to? So at $207.58 per month for 60 months, that comes out to an interest rate of 0.75% per month. What about the future value for annuities? Suppose we begin saving for retirement today by depositing $2,000 per year in an IRA. If that IRA earns 7.5% interest, how much will we have in 40 years? So we have a 40-year number, 7.5% interest, $2,000 is our payment. The future value then of that amount is $454,513.04. We have our calculator formula, our Excel formula, and our mathematical formula. An annuity due, we are saving for a new house. We put $10,000 per year in an account paying 8%. The first payment is made today. So how much will we have at the end of 3 years? Remember, in an annuity due, the payment is paid at the first day of the period. In an ordinary annuity, the payment is made on the last day of the period. Okay? So we see our results here. At the end of 3 years, our future value will be $35,061.12. We have 8% interest, 3 periods, payments of $10,000, and it is an annuity due, so we've selected 1 instead of 0. Perpetuity is when we get payments, regular payments that continue forever. So there's no end to them. That is the present value of the payment divided by the rate. So in this example, we're looking at a current required return. If 40 is our required rate of return, then the rate we're looking for is 0.025 or 2.5% per quarter. So our dividend for preferred stock here would be $100 equals our payment divided by 0.025. That means we would expect $2.50 per quarter. A good example for perpetuity payments is preferred stock payments, which have a guaranteed dividend payout. So this example is looking at preferred stock dividends that pay out $2.50 per quarter as their guaranteed payout per share. We also have the interest rate. So we've been talking about the interest rate. What is the interest rate? So the effective interest rate, or EAR, is the interest rate expressed as if it were compounded once per year. This is the interest rate we use to compare alternative investments with different compounding periods. We also have our annual percentage rate. The annual rate quoted by law. The APR is the periodic rate times the number of periods per year, or the periodic rate equals APR divided by the number of periods per year. When we're looking at interest rates, we always need to make sure that our interest rate and the time periods for that interest rate match. If we have annual periods, we need an annual rate. If we have monthly periods, we need a monthly rate. If we have an APR, or annual rate, based on monthly compounding, we have to use the monthly periods for lump sums or adjust the interest rate accordingly. So we're going to look at the formula. So the APR is the quoted rate, and M is the number of compounds per year. That gives us the effective annual rate of interest. So we're going to look at those functions in Excel. So we have two functions in Excel. We have the effect or the nominal. All rates are entered as decimals, and NPR equals the number of compounding periods per year. Now, you might not have these already available in Excel, in which case you have to add in the analysis tool pack, which you find in Excel under options. So let's look at an example now. We have two savings accounts that we need to choose from. One of them has a 5.25 daily compounding rate, and the other one has a 5.3% semi-annual compounding rate. So we're trying to figure out what the effective interest is. So the effective interest rate versus what it says with the compounding. So the first account has an effective interest rate of 5.39%. We can see from our effective interest formula here that we have the 5.25% interest, the 365 days compounding. If we put it into Excel, we have the effect, 5.25% interest, 365 days compounding. So our effective interest with the first one is 5.39%. The second account with 5.3% semi-annual, so twice a year rather than every day, has a 5.37% effective rate. So we would be better off with the daily compounding, which has a 0.02% higher rate. What is the APR if the monthly rate is 0.5? We then take the monthly rate times 12 for the number of months in a year. If we're trying to calculate the annual rate from a semi-annual rate, then we take it times 2. If we have an annual rate, we are going to divide the annual rate by 12 to get the monthly compounding rate. So how can we compute the effective rate and the annual rate? We look at this. Suppose we can earn 1% per month on $1 invested today. The annual rate is 12%. 1% times 12. How much are we effectively earning? So the future value and the effective rate is 12.68%. Okay, so the effective rate versus the annual rate when we have monthly compounding. What if we put it in another account that we earn 3% per quarter? So quarter is 4 times a year. Then our annual rate is 12% and our effective rate is 12.5%. This is the formula for computing the APR from the effective annual rate. M is the number of compounding periods per year. So suppose we wanted to earn an effective rate of 12%, and we're looking at an account that compounds on a monthly basis. What annual percentage rate must they pay? So we want an effective rate of 12. That's what we're going to use in our calculation. So we need an annual percentage rate of 11.39% in order to get an effective rate of 12. Now let's look at payments with our APRs. What if we want to buy a new computer? The store is willing to allow us to make monthly payments. The entire computer system costs $3,500. The loan period is 2 years, and the interest rate is 16.9% with monthly compounding interest. So what is our monthly payment? We can see here from the calculator calculations, it gives us a monthly payment of $172.88. This is the payment formula in Excel. If we make 24 payments of $172.82, we pay in the end over 2 years $4,149.12. So we're going to pay $649.12 in interest above the cost of the system. How do we calculate future values with monthly compounding interest? So suppose we deposit $50 a month into an account that has an annual rate of 9% based on monthly compounding interest. How much will we have in the account in 35 years? $50 every month at 9% interest, compounding monthly. We have the future value result here, 420 payments. So that's the number of payments we make, $50. This is the monthly compounding rate, 9 divided by 12. So the future value in 35 years is $147,089.22. What is the present value? So if we need $15,000 in 3 years for a new car, we can deposit money into an account that pays an APR of 5.5% based on daily compounding. So how much do we need to deposit? So our rate is 5.5 divided by 365 because it's an annual rate daily compounding. We are only making one payment of $15,000. That's our future value. So the present value of that is $12,718.56. When we look at pure discount loans, a treasury bill is an example of that pure discount loan. The principal amount is repaid at a future date and no periodic interest payments happen. So these treasury bills, savings bonds, some government bonds have these. You don't get any payments and you just wait until the bill is its full amount. So we have if a T-bill promises to repay $10,000 in 12 months and the market interest rate is 7%, how much will the bill sell for in the market? So we don't get any interest payments. We're just going to get $10,000 in 12 months. So we can see here that the present value of that is $9,345.79. It's often that government investments don't make regular interest payments. They just are discounted back and give you a lump sum in a future time. What about an amortized loan with a fixed payment? This is common for car payments and mortgage payments. So each payment covers an amount of interest and reduces the principal. If we have regular payments every single month, what is an annual payment? So we have the interest rate is 8%, the principal amount is $5,000, and it's a 4-year loan with yearly payments. So we have 4 total payments, 8% interest. So our payment is going to be $1,509.60. We're going to make 4 equal payments of $1,509.60, and that covers both the $5,000 and the 8% interest for 4 years. This is an example of an amortized loan table with a fixed payment. So we have our beginning balance, our total payment amount, we pay $400 in interest, and we pay in principal. So the principal goes down each time, which means that we pay less interest. The more that you pay on an amortized loan, however long the loan comes out, so think about a 30-year mortgage. For a 30-year mortgage, that those payments at the first are high interest and low principal. So if you overpay, you will pay off faster and you'll pay less interest because your payments initially are more interest than principal amounts.